seventh embodiment, we found the best voltage to be attained from the system of using 3 pancake coils. As one can see, the middle pancake coil here has 2 coils up and below it. On each of them coils we have voltage meters. The top secondary coil is referred to LS2. The bottom is LS1. Each of these resonant tank loops in space pick up a voltage and circulating current. The idea here is then, to the right of those 2 loops, we've made a connection which of series those voltage rises, and on the right hand side we have a 340 volt output attained to in this method prior to energizing the field, which is the highest voltage that we have seen in placing these pancake coils and 67:1 turn ratio fine wire secondary coils. These secondary coils are 2.4 Henry, 140 ohms, and they are balanced by 50 nanofarad capacity. Now what we want to do now is we have the system functioning in the non-field range, and we've got a meter on LS2. A little bit of extra background lighting there. LS2 is reading in the vicinity of slightly over 200 volts. Now we're going to look at the voltage on LS1. That should tell us that's the bottom coil's voltage. And we have 158 volts on the bottom. And now we're going to look at the voltage across both of them potentials, and we're going to wire that meter up across both of them potentials. And we note that that voltage is in the 300 volt range. And it is the addition of the previously measured voltages, thereby making assurance that each of them voltages are being created oppositely in time, and combining to get the best results obtainable. So looking now for the right hand meter read, which we'll be doing here, hopefully it won't be shot with this. We have the face of a magnet here. This demonstration is going to show the differences between straight neon as a load on this system and a ballasted neon as a load to the system, which we can do by adding the intervening resistance of the ceramic magnet in series in the circuit. Right now we should be able to see 364 volts being procured through the process, with 1 volt one side reading 207. We assume the other 160 is coming from the other side in addition. Now then we're going to go in there and turn up our field. We're going to turn up our field until we get neon discharge. We're going to note our preliminary conditions. And now we're going to note something very strange about the system. One would think that since the third coil is spaced apart from the primary 4 coils we're using in the system, then its influence on the system will be more or less minimalized. Watch what happens when we change that coil and turn it over. We're at 0.41 stator, 0.78, 0.90, red meters in the background. The phase amperatures are 0.48, 0.34, and 0.63 on the top. All in a 8.8 to 1 volt input. Now we turn this top coil around. We've got 0.40 and 0.30 on our power phases. Now we've got 0.28 and 0.24 on our power phases. So as one can well imagine then, and of course our output voltage went down. So we can see that that third coil, even though it's out in space, has an influence on the system. So go back and put that to the correct orientation. Note that its amperage went up also. It's 0.74 is incorrect, and 0.64 in the correct position. Having noted that, we'll go back to our discharge point. One can imagine in the magnet, in a certain sense, will probably try to quench the arc and push the arc aside, and it probably gives it more filament resistance in the discharge. But there's quite a big difference between the unballasted and the magnet ballasted version here. Here we're getting a pretty efficient performance with 280 volts across the entire process. This is very low voltage. See, it jumped up there. It went up to 469 volts when the discharge ceased. So we can see that the discharge is loading the process down to about half of its output voltage, making it a maximum energy transfer in a good range thereof. We see on the top coil, we're able to read voltages in the 150 volt range, 250 volts across the entire process, which will jump up to 500 volts once the arc is extinguished. Now we'll quickly note our operating circumstances for that scenario. We're drawing a little over an amp on our stator lines. 0.7, 0.5, 0.9 amps on the top coil, and 1.3, 1.4 volt operating range. Now then, we'll go ahead and finish out here by showing the unballasted version. The ballasted, pardon me. Whereby we simply unhook the circuit from that side of the source, and now hook it to the steel ruler off of the magnet source, and note the more controlled discharge now. Now I'm still looking at a pretty good efficiency anyway, and we have forgot to mention one thing. Now we even got an amperage meter in there this time. Got a pretty steady state, 2.2 milliamps in that circuit. 0.18. And this is the entire power source then that we used to power the bipolar Tesla coils. Let's look at one shot of our amperage in. Here is our input conditions. input. Well, it's hard for the camera guy to see, and me myself, how well the pictures come out. And then again, we'll briefly note that this is the power system to be employed on our dual bipolar Tesla coil system, and we'll stop from there.